Hi there, I'm Ken Thompson, and in this short video cast I want to share with you some new tools and techniques I've been developing for making radical improvements to business processes. I call this approach process physics because it looks at a business process mathematically and uses simulation technology to find just how much money is being left on the table, and more importantly how to reach it by finding the process's sweet spot. Now the first step is to create a rigorous model of the current process. Now by rigorous I mean a model which recognizes that the financials are the outputs generated by the inputs and the structure of the process. This is radically different from the spreadsheet view of a process, where basically you can, if you like, have your sales doubling in February from January without any consequences. This model that I'm building it on is self-consistent in that outputs such as sales and profit have to be derived from the activities of the model. So I'm going to illustrate it with a sales process as shown in the diagram, which shows new suspects coming into a business, a percentage of those becoming qualified into prospects, a percentage of those actually becoming customers, and depending on how well they're engaged with, they remain either active customers, inactive customers, or ex-customers. And inactive customers, active customers, and new customers each generate revenue per month and cost per month and thence profit per month. And some of these boxes are what we call conveyors, in that they have a certain time. It takes a certain time for a new prospect to become a new customer, and that's what the little triangles mean. So the first stage is to create a precise model of the process using the inputs and the structure to create the outputs. Now once you've done that, what you can then do becomes pretty powerful. So we have here the simulation dashboard, and it splits into a number of areas. On the top left, under key sales results, it shows the performance month by month against a baseline. Below that we have a summary simulation of the various states of all the different objects in the process. Below that we have what we call the key process lever values. For example, the number of suspects coming into this business is 100 per month. Then on the right hand side we have the means to change these key lever values. For example, if we want to increase the number of suspects by 50%, we just move the lever up to 50%. Likewise, we could decrease it by 50%, and you can do that in each of those levers, as you can see. So you have 14 levers, and by making changes to the levers you then change the performance of the process. Then when you want to try out a simulation, you just hit the run button, and there literally in real time it goes through and executes 12 months very quickly indeed, and gives the results. So we're on the baseline at the minute. So what you would normally do first of all is a few kind of standard tests. The first test would be, what if we improve everything by 1%? And we run that through, and we can see at the top that that produces a profit of 14.6 million, whereas the profit we've got on the baseline is 11.2 million. So that's interesting. The software is clever enough to work out actually that if you're increasing if you're improving a time, you reduce it. If you're improving a cost, you reduce it. But anything else, if you're improving it, you generally increase it. So that's the first thing we can do in terms of finding extra potential in the process. Now, the second thing we then can do is to, let's imagine you put a lever up to its maximum level. And we can do that for every single lever, and then we can put it down to its minimum level automatically. And when you do that, you get a little graph like this, which says, for example, the most positive impact levers, and typically it's usually the two financials, and sometimes we can discount that at this stage. But very interestingly there, if you look at management rate, you'll see if you push that up to full by 50%, you'll increase the revenue, the profit, from 11.2 million to nearly 24 million. So that's indicating the kind of things where you should be applying your resources to. And then also, if you look, for example, at something like resuscitation rate, that doesn't make so much difference right down at the bottom there. So these are areas you can be relaxed on and actually move resources into the higher profit areas. So that's one half of the story. Moving on down, then we push the individual sliders down to their minimum, see what that does. And we can see, for example, if you put management rate down, the profit goes down from 11.2 million to just under 1 million. So these are areas you must protect. So the objective of this little analysis, which is done automatically, is to classify things into 4 areas. Things to be increased, things to be protected, things to be maintained, very importantly things to be relaxed, which create resources for the other areas. So that's the first bit of analysis and looking at how we can improve this process. Now let's go back to the model again. Now the other way we can improve the process is by using the power of simulation technology to do bulk simulations of multiple runs. And what we can do is we can specify a series of random inputs, and I'll just show you what that looks like here on a randomizer, where basically we've got the 14 different sliders along the top, and we can specify, in this case we are holding development rate, management rate, retention rate, and we're letting the rest spin free under random control. And we create a little simulation of 200 different scenarios. We then run that through the simulator, and that takes about 2 minutes, and when we refresh the results we see that we start to identify higher return scenarios. For example, that top scenario there, turning in a profit of not 11.2 million but 27 million, but we're having to consume quite a lot of resources to get there, 60%. But if you look on down and move on down that table, you can see there's some other scenarios. For example, we're creating 26.4 million with very little extra resources. So for the technically minded, this is called genetic algorithms, where what I would do then is I would pick a solution I like that one there, and then I would breed new solutions from that by fixing some of the dials. So it's a bit like playing the one-armed bandit and holding various combinations when you're able to hold. Now you can see that you can get some rather significant results when you start to do this, getting your profit up from 11.2 million to 27 million in that example. So the final thing I'll show you here is price and demand. There's always a relationship between increasing price and the effect on demand, and generally if you increase price, your demand will go down. So there is what I would call a price demand sweet spot, and we can again use this, the simulator automatically to find the price demand sweet spot. And in this example here it shows that if you leave the price static, it's 11.2 million. If you put it up 2%, your profit actually goes down by 250 million nearly because of the impact on demand. But if you reduce your price by 2%, your profit actually will go up. Now this relies upon you having a good understanding of how price relates to demand in this particular process. So that's all I want to really show you at the minute. It's a short introduction to a new discipline which I call process physics, which is looking at a business process mathematically, understanding the structure, and then using simulation technologies to find what are the opportunities, what revenues being left on the table, and more importantly, how can I get that revenue. If you'd like to find out more about this, then visit my blog www.bioteams.com, and I'm Ken Thompson at bioteams.com.